So now let's go and put it in a picture. I've just talked to you about how it is that I've just done a diprotic acid titration. It was a diprotic acid titration where my pK values were 4 and 10, and I was titrating with a strong base and measuring my pH. Now, this is what this thing is going to look like. Let's think about why it looks like this. It looks like this because unlike a monoprotic acid case, I don't have just one equivalence point. I have a second equivalence point. I have two different places where the pH spikes considerably. What else is true about this? I don't just have one flat region where the where the pH doesn't change. I've got two, making this a two-buffer system. I can even tell you exactly what the values are for these pHs here. This one's going to turn out to be right about pH 4, and remember this one's going to be right about pH 10, and we'll remember why in a second. But let's work our way through the titration. We start off with no hydroxide added. This is just a beaker filled with H2A and KaCa to the 1/2, using this pK value of 4 here as the answer. Here I am in my first buffer region. I've got H2A and HA minus. So that's a nice buffer built around the first K value. H plus equals Ka times Ca over Cb. Remember that if I'm at the halfway point here and I read over, the pH is equal to the pK value, and I know that value right there is equal to 4. When my pH first starts to spike, it starts to spike as I reach the equivalence point, and at the equivalence point I'm filled with only HA minus. But remember that HA minus, it can lose protons and go this way, it can gain protons and go that way. Consequently, I have to take into account both of the K values, and there's a nice simple amphiprotic case solution, which is to add the two K values together and divide by 2, or to multiply the two and take the square root. I continue on to my next association, and as I start to do it, I realize that I have entered a second buffer region. That second buffer region corresponds to the second pK, the more basic pK. Once again, the halfway point from this dissociation right here reads back to a pH of 10 because the pH equals the pK at the second dissociation, halfway to the second dissociation. And then I get to this point right here, the second end point. Here I've got A double minus. That's quite different than this first point here, because this right here can't go both ways. This right here is a weak base. And because it's a weak base, I need to do a weak base calculation. So I convert the pKa into a pKb and do a simple OH minus equals Kb Cb to the 1/2 problem. And then finally, I get to the region where I have excess hydroxide, and now I am doing a strong base calculation. 1 region, 2 regions, 3 regions, 4 regions, 5 regions, 6 regions. One of the regions is a weak acid, 2 of the regions are buffers, 1 of the regions amphiprotic, 1 of the regions weak base, 1 of the regions excess strong base. You see why people who teach this stuff love titrations. Everything about acid-base chemistry is resonant there. And why we particularly love the diprotic acid case, because I can cover everything you need to know. Strong, weak, buffer, amphiprotic, and it's all sitting right there. The only thing that makes this complicated, the only thing that makes this difficult, is that you look at these compounds here and can't turn them into this. Or that having turned it into that you can't assign the appropriate K values to them by looking at the kinds of species that are present. Once you can get that part down, then, as you see here on this titration curve, the problems are really evident, and the calculations are no more difficult than when you were working in the monoprotic cases.